Okay, so yeah, we are live. Uh, okay, so hey everyone, this is our second stream for RISC Zero, and in this stream we are going to explore more in details what RISC Zero is, and uh, yeah, I mean just try to play with it, create basic program of RISC Zero. To be honest, I also don't know much about RISC Zero, so it's part of exploring RISC Zero from somebody who's just purely interested in the ZK technologies and was just want to see like top projects, how they do, and what are basically some of the top applications that are built on top of them. So yeah, let's start exploring RISC Zero. Okay, so just to recap, we created a basic version of the RISC program in our last stream, where we essentially created this method in guest, where we were like doing this thing called essentially reading the inputs. I think this was not here, but we were doing it in the template, so I might have wrong folders open. So we must be on RISC Zero, CD RISC Zero. Yeah, CD examples. Okay, and we had the thing here. Which one was, I guess, hello. This one, hello world, where we changed this example for multiply, or we were doing something different. So yeah, so this is what we did. We changed this to change this so that it does now age verification, if I am correct. So that's how we changed the method, and we must have this age verification thing now here. Yeah, age greater than 18. Yeah. Okay, so let's see what else we can do with the RISC Zero. Let's go through it again. Quick start was done. Hello world tutorials, building ZKVM, hello world, building ZKVM, hello world. So this tutorial will walk you through building your first ZKVM application. By following the steps in this guide, you will learn how to use the Cargo RISC Zero tool to create a new project. Okay, I believe this documentation, to be very honest, this is not like the flow is not really in a rhythm. So like here they say that you start a project by doing this Cargo RISC Zero new, and then they immediately switch on to running the example with this example, right? That's what the thing is. But anyway, that's what it is. I don't know if this will work, but let's just see if this thing works or not. Okay, so CD RISC Zero dummies and CD hello RISC. Okay, cargo run -- release. I'm just checking if it works or not. So in this guest method, it is just taking the input. Okay, it is not doing anything with input at all in this guest method, and here we are not doing anything at all. That's the code for the guest method and these methods, and I think everything we are doing is in the target method. Executor environment, builder, default prover, and Yeah, default prover. Executor environment, prover, default prover, prover dot prove, guest code for proof, zkelf. And this one was methods, guest code for zk proof. Hmm. Underscore elf. So that is fine. let's try to let's try to see how we can change our example, uh, some other example. Let's take some other example from here. What about this password checker? Hmm. So in this password checker, what are we doing? Hey, this is bit of a complicated code. Hmm. Okay, and this is all seems very scary to me, to be very honest. But let's go through it one by one. Optimizing your zkVM application, that is understanding IO. Okay, let's go through this one. Understanding IO into the zkVM. So in the Hello World tutorial, we had a brief introduction to how to perform IO operations in the zkVM. Okay. So just to recap, we can provide the input to the guest program with the environment variables. Okay. So in the Hello World tutorial, we had a brief introduction to how to perform I/O operations in the zkVM. Now we will dive deeper into the subject. Keep reading to learn more about what are the different types of data in the zkVM, how to handle inputs and outputs, best practices for handling I/O in the zkVM, setting the stage. We can think of programming in the zkVM as uh, okay. So in the Hello World tutorial, we had a brief introduction to how to perform I/O operations in the zkVM. Now we will dive deeper into the subject. Keep reading to learn more about what are the different types of data in the zkVM, how to handle inputs and outputs, best practices for handling input output in the zkVM, setting the stage. We can think of programming in the zkVM as transitioning between two worlds: the host, where computation works the same as in any other regular program, and the guest, where computation is done in a zero knowledge environment. Okay, since the guest works in a GK environment, it has access to a limited set of ways to get data if compared to the host. The only way to send data between the host and guest is through executor environment. Okay, so I guess we already have seen that how this executor environment essentially will work. Like these are the this is the guest code, and we are getting this age input from the host environment, and the way we are passing this age input from the host environment is like this. Okay, uh, not here exactly, but here executor environment builder dot write a. Okay, such such data transfer is done through file descriptors. Such data transfer is done through file descriptors. The zkVM specifies four default file descriptors: stdin, stdout, stderr, and journal. They are defined in the file number module. The zkVM data model. The ZKVM has a data model that distinguishes between public and private data. By public, we mean data that is included in the journal and becomes part of the proof. while private data is only accessible by the host and guest. What does it mean? The ZKVM data model. The ZKVM data. The ZKVM has a data model that distinguishes between public and private data. By public, we mean data that is included in the journal and becomes part of the proof. Okay, so that means this data will be accessible by the verifier, while private data is only accessible to the host and guest. Okay, so this is like a public input and private input. If your application handles sensitive data, it is important to be aware of specifically which data is committed to the journal, avoiding any sensitive data to be included in the proof. That makes sense. This is like typical ZK thing. Sending data from the host to the guest. There, the stdin file descriptor is used to send data from the host to the guest. In the host, it is possible to set the input data in the executor environment through the methods write and write slice. Okay, the guest has corresponding functions read and read slice to read the input data. Okay, writing to the guest's stdin can be done as simply as code below. For a real example, check the voting machines example. What is it saying? Sending data from the host to the guest. The stdin file standard input file descriptor is used to send input data from the host to the guest. In the host, it's possible to set the input data in the executor environment through the methods write and write slice. The guest has corresponding functions read and read slice to read the input data. Okay. Okay. Writing to the guest standard input can be done as simply as the code below. Okay. Since we mentioned the read-write methods and their slice variants, let's take a moment to understand the difference between them. A note on performance. During the process of sending data from host to guest and vice versa. During the process of sending data from host to guest and vice versa, can either do so while deserializing the data or by sending raw files. A note on performance. During the process of sending data from host to guest and vice versa, we can either do so while deserializing the data or by sending raw bytes. It's a trade-off between convenience and performance. By using the standard functions read, write, and commit that we will cover in the next section, the ZKVM performs automatic deserialization of the data. This enables easy handling of complex data structures, but it comes with a performance cost. Using the underscore slice variants, on the other hand, allows for sending raw bytes, which is faster but usually requires less ergonomic code. So it is saying during the process of sending data from host to guest or guest to host, we can either do so while deserializing the data or by sending raw bytes. It's a trade-off between convenience and performance. By using the standard functions read, write, and commit, the ZKVM performs automatic deserialization of the data. Deserialization of the data. This enables easy handling of complex data structures, but it comes with a performance cost. Using the underscore slice variants, on the other hand, allows for sending raw bytes, which is faster but usually requires less ergonomic code. It is good practice to use the standard functions first, switching to the underscore slice variants when performance becomes an issue or when optimizing the code to save on cycles. Since both approaches can be used concomitantly, moving from one to another shouldn't be a problem. We have a more detailed explanation on guest code optimization if you want to learn more about this topic. Okay, sending private data from the guest. sending private data from the guest. Back where we were, after getting data from the host and performing some transformations on it, we might want to send private data back. Both std out and std error file descriptors are used to send data from the guest to the host in a private manner. And a convenient way to send data to the host std out is by using the write method. Okay. After getting data from the host, performing some transformations on it, you might want to send private data back. Okay. On the host side, it is possible to read data coming from the guest by reading the buffer that was originally passed to the executor environment through its methods std out and std error. The private data alluded to here is not included in the proof, but it is accessible to the host. This means that the party generating the proof can access the data, so you should take this into the consideration. If you don't want to let private data leak to any other party, it is possible to achieve full secrecy by proving locally. Good practice to handle sensitive data is to use proof composition, essentially splitting the proving process into smaller parts, proving the sensitive data locally and combining the larger program data through composition in a capable proving service like Bonsai to speed up the proof generation. Sending public data from the guest. We saw how to send private data directly to the host, but we might also want to commit public data attesting to some fact that we want to share with the world. We can do so by sending this data to the journal file descriptor. This data will be included in the proof and can be accessed by any party through the RISC. Okay, so I guess we got this basic idea of what we can do. So I guess the next step is be writing the things on our own. Okay, so what are some examples that we can do? So there is the hello world, there is this chess example. Okay. Let's first see what this Bonsai application is. The remote proving. I think we still have to get our Bonsai, keys. Let me just check privately if I have got the Bonsai key. I applied for the Bonsai key, that's for sure. Not right now. So the Bonsai keys are not here right now, so we can definitely use local proving or something different. But let's try to see what example that we can run. I am more okay. This is very this is interesting. Okay, so let's try to build this example voting machine on RISC Zero. A simple voting machine built on the RISC Zero platform. This example is for educational purposes only, not for use in actual elections. A voting machine is a state machine with three operations: initialize, which officials use to configure the machine; submit ballot, which voters use to submit their ballots; and freeze, which reveals the current vote count and puts the machine into a state where it is no longer accepting it. Okay, so this looks like a project that we can build from a scratch. So I'm going to just move this here. And I'm going to basically start fresh essentially. Okay, so what we are going to do here, mkdir voting my silly, okay, monkey voting, monkey votes machine. Okay, we are going to make a voting machine for monkeys. Okay, uh, and we are going to do it from scratch. That's the idea. Like, we are going to type out a lot of code, and yeah, I mean, we are going to see how everything is there. Okay, so readme.md, voting machine for monkeys. After all, monkeys should also be able to vote. But the thing is, monkeys hold grudge against their fellows for a long time. Okay, so you want this voting to be anonymous. Next leader of this monkey pack will be decided by this anon voting. Okay, so we have a lot of monkeys. Okay, so we have these monkeys. Okay, so let's go. Okay, so in this machine we have initialize, underscore initialize. Okay, current pack leader creates a this voting process, submit ballot, submit vote, submit ballot. Okay, let's keep it vote. Okay, submit ballot. All monkey, including kid monkeys, cast vote, choose their next leader. Okay, and then we have a freeze, stop the votes, voting. Okay, so this stop voting is essentially reveals the vote count, and no more voting, and we have a new pack leader. Okay, so this is great. I mean, we have this basic structure of this thing. Okay, so what are we going to have this here? Okay, so we have something called cargo toml here, cargo dot toml. Okay, so we have this cargo toml here. Okay, I'm going to increase the size here as well. Okay, so we have this package, and not this package, and we have a monkey voting machine, monkey voting app. Okay, so we have this monkey voting version is equals to, that's fine. We can find the edition as well, and we can define the edition as 2021. I'm going to use the same that was there. uh, what are some dependencies we have? So in terms of the dependencies, okay, so we are going to first of all define the dependencies, okay, and dev dependencies and features. Okay, so we have these three things. In terms of dependencies, let's define tracing. Okay, tracing as a dependency, not like this. Tracing is equals to version equals to 0.1 and features is equals to log. Fine. Now we need to also define this RISC Zero ZKVM dependency, and let's see what version we can define. Okay, so not here. Host, inside the host. Okay, so RISC Zero version we can define as 2.1.0. Okay, 2.1.0. Carried 2.1.0. Okay, now what? So we have tracing and we have RISC Zero ZKVM. Now we can define dev dependencies. We need X dependency, though I'm not sure why, but we'll figure it out. We need test log dependency. Okay, so we need test log version equals to 0.2, default features equals to false, and features is equals to trace. Okay, this is just for okay, tracing subscriber, okay, that is version 0.3. okay, and features is equals to environment filter. Okay, and here we are going to do CUDA for RISC Zero. This is for I guess GPUs, if I'm correct, ZKVM plus CUDA. Default is equals to empty array and prove is equals to RISC Zero ZKVM f/prove. Okay, so let's see if this is all good or not. So okay, tracing subscriber, we also have SERDI here, but I guess that is fine. Okay, that is cool. Now, so this is like a host and this is a guest thing, but anyway, now what are we going to do next? So next we are going to do, so next we are going to create a core. Okay, so we are going to create a voting machine core. Okay, so here we are going to create a folder core. Okay, then we are going to essentially I'm just trying to figure out what are these things that I have. Okay, okay, so let's first write down the core. Okay, so core is in itself like separate Rust project. So we have cargo.toml, okay, package, and then we have name equals to, let's say, funky voting core, okay, version equals to again 0.1.0, edition again 2021, okay, and then we have dependencies, okay, and we have this dependency of RISC Zero ZKP, okay, and I'm not sure what this dependency version would be, but I can define it as this one, but I'm going to ZKP, no. Okay, so I'm going to search this for uncrates.io. Okay, so we have these crates, which is like a lot of crates. Okay, so we have this. No, I mean, as was 2.0.1. Okay, so we can add 2.0.1. I guess their version goes the same. Okay, this is 2.1.0. And what about this version? RISC Zero ZKVM. Just to search RISC Zero ZKVM. 2.1.0. This is their latest version. Nice. Okay, so let's try to see what else we need in this RD. Here we just do default features as false. Okay, SRD serialization deserialization library version equals to 1.0. Okay, and default features equals to false. Okay, what I'm missing here? Okay, the comma is missing here definitely. I also want to see what this RISC Zero ZKP is. I am thinking this. These are the core algorithms that prove and verify the execution of ZK Stark circuits. Okay, CUDA metal proof STD. Okay, and these are, I guess, the docs, the RISC Zero proving system, modules, adapters, and okay. So we have SRD and we have this, and now we are going to write a code. So this is going to be a library, so I'm going to create a src. I don't know if this is visible, but yeah, src lib.rs. Okay, and okay, so what are we going to do here? Again, I'm not even sure, but we are just going to type a whole lot of code. I mean, that's something that makes sense. Okay, okay, so there is a macro CFG. Okay, by the way, I'm typing by just looking into this secondary screen, so I'm not typing like just some random thing. Okay, not test, no STD. Okay, so no standard input and no test. Okay, so use RISC Zero. First of all, we are going to define a voting machine state, and for that we will use SERDI. Okay, deserialize, serialize. Okay, and we are going to define a pub voting machine, monkey voting machine. I'll just say monkey voting machine. Okay, we just keep voting machine state. What is this voting machine state? First of all, is the voting open? Polls open, which is boolean. Okay, what else? Voter bit field. Okay, voter bit field, which is U32. Okay, and pub count U32. Okay, and we need to provide some attributes here. Derive. Okay, clone, debug, deserialize, equal, partial, equal. Okay, serialize. That's fine. So we are doing this: clone, debug, deserialize, equal, partial, equal, and serialize. Okay. Now we are going to do implement voting machine state. So we are going to write some methods on this struct. Okay, PowerFan vote. Okay, so in the vote we just provide mutable reference, voter U32, vote yes, cool. Okay, let mute vote counted is equals to false. Okay, let voter underscore mass equals to voter. Okay, so this is a left bitwise left shifting. Okay, so let's see. This is interesting, but bit complicated as well. Okay, if self dot polls open and self dot voter bit field is equals to 0 and voter mass self dot voter bit field This is a bit interesting. What is this? Okay, I don't even know how to. Okay, voter dot mask. Voter mask. If vote show yes equals to, if vote is yes, self dot count plus equals to 1. Okay, this is only a voting for, okay, vote counted equals to true. And just return the vote counted. This is very interesting though. Vote counted. Though how it is working, I am not sure. But this is something okay. What is this vote mask kind of things doing? Is this a sort of a voter ID? Okay, let's take the help of LLMs. Explain this Rust code to me. Specifically, this part. Let's focus on the part. Okay, voter mask. This line creates a bit mask of the current voter. Shifts the binary number 1 to the left. If the voter is equals to 3, voter mask voter mask. Okay. Voter mask. Okay, so first of all, we made a mistake here. 0 is equals to correct. You are right. The second line is bitwise and okay. Explain this line to me in detail. Detail. Okay. Oh, okay. Suitable market. Okay, that's fine. So we are first of all creating a mask here. So it will be like 0b 00000 something, you know, 0000000. 100. Okay. Okay, this makes now a bit more sense. Okay. Wow, what a nice score. Okay, so okay, let's continue. So we have this voting machine state. Now we are going to create a new struct. Struct initialize voting machine commit. Initialize voting machine commit. Okay, polls open boolean. Okay, voter bit field u32. Okay, state digest. Okay, where we got this digest from? Okay, so this digest thing is right now not there. Why this Rust analyzer is not working? In the cargo.toml we have this thing. Okay, and we can reload the window. No targets. Okay. Why we need a target? I'm not sure. Can't we just define? Okay, so let's do one thing here. Just define it here as voting machine core is equals to path equals to core. Okay, Reload the window. No, it's still failing. That's fine. Let's keep doing this. So we have this voting machine. We have this initialize voting machine commit. We can also derive things on this. We can derive debug. That's fine. Deserialize equal, partial equal, and serialize. Okay. And then we define struct ballot of voter U32 for vote yes boolean. Okay. And we can derive clone, debug, deserialize equal, partial equal, and serialize. Okay, construct ballot. Okay, now we can define submit ballot commit. Okay, I'm just again going to see fail to load workspace. This is disastrous. I guess I get it. New file folder src, new file lib.rs. Okay, so I guess now this works fine. Okay, so we have this what do you call, voting machine for lib.rs. Okay. Now we have created a ballot. Do we get any error here? SERDI, serialize, deserialize. Okay, and where do we get this digest thing? We haven't mentioned this digest thing still. State digest. Okay, so that's fine. We can use RISC Zero ZKP core and digest. Okay, no method package named voting machine core font. That's fine because monkey voting core is the package name. So that's how we will find this package. Okay, so we have now this. Now we are going to create another struct, pub struct, submit ballot commit, submit ballot commit. Okay, pub hold state digest, pub new state, which is also digest, pub polls open boolean, pub voter bit field U32 of voter, U32 of vote yes, boolean of vote counted, boolean. Okay, and we are going to derive few struct. Derive. Was just wondering if debug, deserialize, and equal, partial equal, serialize. Okay, so we have old state, new state, false open, voter with field, voter yes, vote counted. Okay, and we also now have submit valid params. Submit valid params of state, voting machine state of ballot. Okay, and derive, clone, debug, deserialize, equal, partial equal, serialize. Okay, that is for the submit valid params. Subtract submit valid result, okay, state, voting machine state, okay, and vote counted. Sure, why we need so many of these things, but anyway, one step at a time. Vote yes, boolean. Okay, and we need again the attributes on this. Derive, okay, derive, this is the result thing. So clone, debug, deserialize, okay, equal, partial equal, and serialize. Nice. Okay, clone, debug, deserialize, equal, partial equal, serialize. So this is what we do have so far, which doesn't make much sense to me apart from this voting thing, but anyway, now we are going to implement this submit valid params. Submit valid params. Pub fn new state, voting machine state, ballot self. Submit valid params. What does it take? State and ballot. Okay, state and ballot. So this is for a new, and PubFN process and self. Submit valid result. Let me move state is equals to self dot state dot clone. Okay, let vote counted is equals to state dot vote self dot ballot dot voter. valid dot vote yes. Okay. Submit valid result state put counted and vote yes. Self dot valid dot vote yes. Okay. This takes previous state into the consideration. This is for proving the thing. Like there is this state machine sort of going on. Yeah. Now obstruct freeze voting machine commit. Derive, debug, deserialize, equal, partial equal, serialize. Hold state, which is digest, of new state, which is also a digest. Polls open, which is boolean. Voter bit field U32 count U32. Okay, this is great. Now let's see obstruct freeze voting machine params. Obstruct freeze voting machine params, and we are going to derive here again the same thing. Freeze voting machine params, debug, clone, and deserialize, equal, partial equal, and serialize. Okay. Pub state, voting machine state, freeze voting machine result. Freeze doing. Okay. Obstruct freeze voting machine result. So let's just recap. So we have this voting machine which have three properties. This struct have three properties: polls open, voter bit field, and count. Then we implement a vote method on this voting machine. That is fine. That's the basic machine. Initialize voting machine commit, polls open. Okay, then we have a ballot and submit ballot commit, hold state, new state, polls. Okay, submit ballot params, state and ballot. Submit ballot result, voting machine state, submit ballot params, new process. Okay, submit ballot result. Okay, freeze voting machine commit, freeze voting machine result, pub state, voting machine state, and again we need all these parameters: debug, clone, deserialize, equal, partial equal, serialize. Okay, next we need to implement freeze voting machine params. with a new state, voting machine state, self, freeze voting machine params state. Okay, for fan process and self. Okay, freeze voting machine result. Let new state self dot state dot clone. Okay, state dot false open is equals to false. Freeze voting machine result state. Okay, so this is essentially the core of it that I'm able to understand a little bit, not too much. It's essentially the voting machine and freeze voting machine thing, but yeah. Can I do cargo build here? Cargo check. And can this cargo check will fail? Okay. What about cargo compile? Okay, cargo compile is nothing. Cargo run. Okay. A bin target must be. So cargo check and cargo build is there. Okay, so just cargo check. Fine. So we have this core library now. What else? We can have this methods, new folder methods, and we will have a new cargo.tml, new file cargo.tml. Okay, here with the methods. What did we name our voting machine code, voting machine methods? So we have a package. Okay, name equals to voting machine methods, version again, that's fine, edition 2021. Okay, here we define package.metadata.RISC Zero methods equals to guest. Okay, and build dependencies, RISC Zero build equals to let's see if there is a RISC Zero build dependencies here in the methods. 0.2.1.2. okay, version equals to 2.1.2. okay, so that is for the methods. Okay, do we have a build.rs here? Okay, we have a build.rs. So we are going to create src, new folder src, and new file here, again just build.rs. Okay, and here new folder named guest. So what does this build.rs have? Just fn main RISC Zero underscore build embed methods. I don't have any clue what this is, but we are going to figure out. Maybe we can just search on the documentation. Group composition, REST resource service. Methods, a single main entry point in the GKVM entry point recursion circuit. Okay. Do we have a good RISC Zero tutorial? Creating your first we have it, but it's not really that good, I guess. There's just a multiply method. I ought to create something good. Embed methods. Let's just see if ChatGPT can answer why it is. The embed methods are some suggest for REST methods that you are annotated. Okay. Oh. Well, ChatGPT is pretty advanced. Nice. Okay, so let's see. Embed methods. We have written the embed methods, that is build.rs. So essentially what we'll do is, normally this function is placed inside the file name build.rs, which is a special build script in a Rust crate. Okay, so embed script is using the RISC Zero build kit, which is the part of the RISC Zero ZKVM. RISC Zero build is a built-in crate used for preparing ZKVM guest methods programs that run inside the ZKVM to be included in the host application. It is usually only used in build.rs files, Rust build script mechanism, not in normal Rust code files. Embed methods, the function RISC Zero embed method searches for guest methods that you have annotated with RISC Zero macros like RISC Zero ZKVM guest, generates built-in metadata for them. Embed the compiled guest methods ELF binaries into your host binary using the include bytes, so that you can later run proofs over them in the host. In effect, it prepares the guest programs to be verifiable by the host side ZKVM. It prepares the guest program. Okay, let me just add a bit of a comment here too. It prepares the guest program to be later verifiable, I guess. It prepares the guest program to be verifiable by the host side ZKVM. To be verifiable by the host side. Verifiable by the host side ZKVM logic. Okay, nice. This is great. Okay, now we can move on to see. Let's create a new file here in src lib.rs. Okay, include concat env out directory plus methods dot rs. Well, what is this line doing now? Include concat. Okay, what is this statement? Okay, I'll just post it. This line include is a Rust compile time macro that includes a generated file methods.rs into your code. env out directory gets the value of out directory environment variable at the compiler. Okay, folder and target debug build. Okay, this macro converts strings at a compile time. In this case, it makes a full path string like okay. This macro includes expands Rust code from a file. It generates method.rs file inside the. Okay, so you never include those constants using. Okay, main code you include your constants using. Okay. When you call RISC Zero build embed methods, this is nice. In a builder, it generates a method.rs file. Okay, so basically I'm exposing this okay, nice, this is great. Yeah, now we have a guest thing, and guest is in itself a new project terminal. Okay, so in the guest we have RISC Zero ZKVM package. Okay, name equals to voting machine methods, machine methods guest, version is equal to 0.1.0, edition to 2021. Okay, this is workspace dependencies or RISC zeros. So we have the RISC zero ZKVM dependency that I can directly paste here. Then we have voting machine, monkey voting code, I guess, monkey voting code, and monkey voting code is path is equals to code. Okay, Okay, so now we have src, new folder src, and I believe lib, uh, src, then bin, and init.rs, new file init.rs. Let me just see. Okay, so we have three files here. Init, freeze, submit. New file freeze.rs and new file submit.rs. Okay, so this is our guest code. We can close all thing. Okay, init.rs. Now for the init.rs, let's write the code. No main. Okay, and this macro of no std, that's also fine. Use RISC Zero, zkvm, guest env, srd, to vector. Okay, to vector, sha, secure hash algorithm, sha256. Okay, so we are going to use sha256 here. Okay, use monkey voting code. Okay, initialize. Why this actually, why this reload is not working. That's fine. No package voting. Voting monkey voting core. Let's clear this. Do we have any error? No. RISC Zero, zkvm, guest, entry, main. Okay, fn main. Let's state voting machine can be read. Here is this voting machine state. We don't found it. Voting core. Oh, that's fine. env.commit and initial voting machine commit. Polls open state dot holds open footer bit field state dot footer bit field state hash words to vector and state dot unwrap okay. Initialize voting machine commit. It's interesting. Why does it doesn't give the error? Anyway, use voting machine, use monkey voting code, initialize voting machine commit, voting machine state. Okay, yeah, let's just see cd methods guest, cd methods guest. Cargo check. Wait a minute. Okay, not initial. Okay, and let's delete them for now. I just want to check if at least this looks good or not. env dot commit. Okay, it should be env. Okay, and okay, fine. Now breeze.rs Okay, same thing. Use no main, no std. Okay, use RISC Zero ZKVM, cache TNB, SRD to vector, and SHA implementation, SHA 256. Okay, and use voting monkey, voting core. Okay, freeze. Why doesn't it give any suggestions? Don't I have Rust format or Rust suggestions or something? Rust syntax, Rust targets. No. Okay, let's just restart it. Okay, so let's just remove this. Okay, monkey voting core, freeze voting machine, commit, freeze voting machine, params. Okay, this 0 ZKBM, guest, entry, main, fn main. Let params freeze voting machine params to environment read. Okay, let result equals to params dot process environment right result dot state. We are just trying to essentially write the code down. Environment commit and freeze voting machine commit, hold state, hash words, vector params dot state dot unwrap. New state is let me just see what this line trying to do. So okay, so we've got this voting machine code, freeze voting machine, freeze we have freeze voting machine commit, which is old states, which is a digest. Digest represents the results of a hashing function. It is always 256 bits of storage, although depending on the hash, it may have additional structures, field elements. Okay. Okay, so new state is hash words to vector result dot state dot unwrap. Okay, and polls open result dot state dot polls open voter bit field result dot state dot voter bit field. Okay, count result dot state dot count. Okay, so we have got this. Let's try to run the cargo check. We have one error. Use RISC env. Env commit use of unresolved module. Guest env. This would be guest env. Sure why Rust is not highlighting the errors, but this is bad. Okay, so we have got the freeze thing in place, although like I'm not sure what this method is. Okay, in following code, let me just see. Following code explain. Okay, this. Explain the main function. Okay, this is a ZKVM guest program written for RISC Zero, designed to run inside a zero knowledge virtual machine. Let's break it down thoroughly line by line. This code reads the inputs. Okay, reads the inputs, a voting machine state and a vote action. Processes the vote, writes a new state, commits a hash of the before and after state for ZK proof generation. It is part of the ZK proof zero knowledge proof system, where the prover runs this in a sandbox and produces a verifiable proof of correct execution. No traditional no name symbol. Okay, this is fine. Environment read. Environment writes our system calls to communicate with the host. Two vector serializes structs for hashing. Implement hash words. Hashes byte arrays using SHA-256. Registers the main function, reads the current function, provide hash of the input. This allows the vector to confirm. Okay. Okay. So two vectors serializes the structs for hashing. It gives a byte array. Okay. Now let's try to do the last method, which is the submit. File submit.rs. Okay, again same thing. No main. No std. Use RISC Zero ZKVM. Guest env. SRD to vector. SHA implementation. SHA-256. Okay. use voting machine core, monkey voting core, submit ballot, commit, submit ballot params. Now I get the RISC Zero ZKVM guest entry, and we have the main function. Okay, for the main function, okay, so for fn main, let params submit valid params is equals to env read, let result equals to params dot process env write, and result dot state commit, submit valid commit, submit valid commit. Okay, hold state hash words into vector params dot state dot unwrap new state implementation hash words and vector result dot state dot unwrap polls open result dot state dot polls open voter bit field result dot state dot voter field voter params dot valid dot voter vote yes params dot valid dot vote yes and vote counted params dot result dot vote counted. So we have this, so that is for the submit. So okay, /lib.rs, this is voting machine state. Let's just see cargo check. Okay, so all the guest code definitely is looking good. Though confusing definitely. Okay, now we can go back here and see how we can do that. Let's take a 5 minute break and then we'll continue with the, you know, now with the rest of the code of how to use this guest, guest, code on our host.